Okay, so this last little section of what we've been kind of talking about with respect to aqueous equilibria is going to go back and just kind of deal with the concept of solubility with respect to solids in solution, right? So we talked about solubility in 151, right? So for example, let's say we had some sort of solid like NaCl, right? So this is solid sodium chloride, it's normal table salt. When you put normal table salt into water, right, so we put it into water, we found in 151 that it breaks down into its ions, right, because again, this is an ionic compound. This is what we frequently will just call a salt. So when you put NaCl as a solid into water, it breaks down into its ions, sodium as well as chlorine, right, and they just float around in solution. And so for things that do dissolve, when we put them in water, water is going to be the solvent for pretty much all of the things that we're going to be looking at. For things that do dissolve, we call those soluble, right? So these guys were soluble. When you put it in water, it broke up into its component ions. Very few of it actually stayed in the solid form. On the other hand, there were certain compounds, let's say like silver chloride, that when you put them in water, actually didn't dissociate, or at least to your naked eye, didn't seem to dissociate into their component ions. Instead, for the most part, stayed in this solid form, right? And so those types of salts, those types of ionic compounds, we termed insoluble. And in 151, the way we knew whether or not something was soluble versus insoluble is we had our little solubility table, right? And so depending on the salt, you would go to your solubility table and you would figure out, well, is this going to be soluble when we put it in water, or is it going to be insoluble and form what we call a precipitate, right? So precipitation reaction is when we really kind of started dealing with this type of things. Okay, so that was 151, right? In reality, with respect to 152, this idea behind something being just either soluble versus insoluble is kind of been undersimplification or underjudgment of the reality of the situation, right? In reality, we kind of get this gray window of solubility where things can be very soluble and things can be fairly insoluble, but something or everything to some extent dissociates into its component ions. Okay, and so we're going to talk about that and how we can measure that in this final little bit of this chapter. Okay, so let's try to start looking at solubility, right? Whether or not things are soluble versus insoluble with respect to something that's very, very, very soluble. So let's go back to this sodium chloride, this salt here. So table salt. Normal table salt we know is fairly soluble when we put it in water. It dissociates into sodium and chloride, and we can tell that because when we put it in water and we stir, the solid seems to go away, okay? All right, so again, with respect to sodium chloride, we get a +1 cation, we get a -1 anion, and we put them in water. There's a reason why water helps them break away from one another, right? So water is a polar molecule. It's got hydrogen bonds as well. So oxygen pulls the majority of the electron density in these bonds towards itself, which creates our little partial negative on the oxygen, and we get a partial positive charge on the two hydrogens. When we put something like sodium chloride in water, the sodiums floating around are going to be stabilized by the negative charge that develops on the oxygens, and the chlorides that are floating around are going to be stabilized by the positive charge that develops on the hydrogens. So as water comes in and surrounds our little ions, we're essentially undergoing something that's called solvation. So water forms this nice little shell with its partial charges pointed in the direction of whatever type of ion it's stabilizing, and essentially it essentially solvates our various charges, okay? So as it solvates, it then allows them to move out into solution, so they break away from the solid and they begin to freely diffuse out into solution. Okay, so if we put something like sodium chloride, which again is a very soluble salt in, it will dissociate, right? And we'll get these floating, freely moving, charged ions, right? So now the question would be, can this go on forever, right? As we add more solid sodium chloride, right? So if we keep adding more solid NaCl to our solution, could this continuously dissolve into sodium and chloride? So if we added an infinite amount of solid sodium chloride, would we continue to see this occur? And so the question, or the answer to that question, is no. Eventually, at some point in time, you're going to reach what is called saturation with respect to your solution, where if you were to add more solid sodium chloride, instead of them dissociating into their ions, they would just settle to the bottom of the beaker as a solid, right? There's a point in time where you can't get any more ions to go into solution, okay? So now, that should tell you something about the reversibility of this chemical reaction. Remember that reversible chemical reactions are governed by equilibrium constants, right? So, this is where we're going to move on with respect to solubility, right? We're going to be talking about this in terms of equilibrium, because again, these reactions are reversible, and they're going to come to equilibrium whenever we reach saturation, okay? All right, so the chemical reaction that we're going to be looking at when we're dealing with this equilibrium with respect to solubility is going to be given like so, right? Where we have a solid dissolving into its component ions. So this would be the reaction, the chemical reaction that we'd be dealing with for the dissolution of NaCl into solution, okay? Again, this is going to be given its own little equilibrium value, and we're going to give this a special little subscript. We're going to call this KSP for the solubility product constant, which is the equilibrium constant that deals with these reactions where you're dissolving a solid into solution. Okay. All right, so with respect to sodium chloride, once we finally reach this saturation point, right, we've come to equilibrium between our solid and our component ions. Once we have reached that point, how large of a magnitude do you think K is for sodium chloride, right? How many of these guys are products of this reaction do you think there are at equilibrium when we finally have reached saturation for sodium chloride? So you think there probably are going to be a lot because sodium chloride is fairly soluble, right? And so because of that, there's going to be a lot of products at equilibrium. The K for this would be probably fairly large, right? So for very soluble salts, our K, or our KSP, is going to be fairly large because, again, there's going to be lots and lots of products at equilibrium. Okay, so now let's consider something that in 151 we would have considered or termed essentially insoluble. Now let's consider some sort of insoluble salt. So let's take something like our silver bromide here. Man, not working well today. Not functioning well. So we've got our silver bromide, right? So in 151, we would have said, well, this is insoluble. It doesn't dissolve at all. But again, that was kind of like a black and white way to look at this issue, when in reality, solubility is kind of all of these various shades of gray, right? There is some dissolution of something like silver bromide into its component ions. It is just very few that actually undergo this dissolving process, right? So if you were to take silver bromide and put it in solution, right, you would get the majority of it not dissolving, right? It would just be sitting at the bottom of your beaker as this solid that doesn't dissolve. But one or two out of, let's say, every billion of these ions actually will undergo this reaction, right? Because again, we reach saturation, we've come to equilibrium, and so there's going to be very few of these for what actually remains in the solid, but some of them will still be there, okay? So again, this is going to be our KSP, right? And so for these guys, things that are fairly insoluble, we're going to have very few of these at equilibrium, right? The majority is going to stay like this. So very few products at equilibrium are going to give us very small KSP values, right? So small KSP is what we're going to see for what we have termed insoluble salts, okay? Okay, so in general, we can use these values of KSP as a measure of the solubility. If you have a very large KSP, that means you're a very soluble salt, whereas if you have a very small KSP, it means you're a very insoluble salt, so you don't dissolve that much, right? And then the smaller KSP will look a little bit later on. In general, the smaller the KSP, the less soluble our salt is. Okay, so now that we have defined what this equilibrium, the solubility product constant is, how are we actually going to determine it, right? So what is going to be our equilibrium constant expression for these solubility reactions? So remember, our K's, so any type of K is always the concentration of our products at equilibrium divided by the concentration of our reactants at equilibrium. And of course, they're going to be raised to their stoichiometric coefficients, right? So this is going to be the reactions that we're going to be dealing with these KSPs, right? So if we go ahead and we plug in the concentration of our products raised to their stoichiometric coefficients over the concentration of our reactants, this would be the overall KSP expression, right? You'd think that, but notice that one of our little things here is a solid, right? And we don't ever include solids in equilibrium constant expressions. So because of that, for all of these KSPs, we will never include the product, or the reactant, pardon me. So the correct KSP for this reaction is not this, but is instead just the concentration of calcium times the concentration of fluoride squared. All right, there is no reactant for these various expressions because, again, it's a solid and we don't include that in equilibrium constant expressions, okay? So that makes KSP really nice, right? You don't ever have to include any type of reactant. All you have to consider is our two products at equilibrium. So in general, all of these KSP expressions are going to take this same form, where we're only going to consider the concentrations of our products at equilibrium, and we're never going to consider the concentration of our reactant because, again, it's going to be a solid. Okay, and so, again, KSP is going to be very similar to Ka, to Kb. These are going to be constants that are going to be given to you, and you can look quite a few of them up in the index or the table at the back of the book, right? So in this little table, we've given you KSP values for a variety of different various ionic compounds, and we'll find that things with very, very, very tiny KSPs are very, very insoluble salts, right? But this degree of solubility is going to vary, right? We can see things that are semi-soluble, right, to things that, again, are extremely insoluble, okay? So there's a wide range of these KSP values depending overall on the salt that we're looking at. And again, this would be a constant that would be given to you. Okay, so now we're going to start talking about a little bit of the differences between what we think of as solubility versus what we've been talking about now, which is KSP, the solubility product constant. So the solubility of a salt is defined as the amount of salt that will dissolve in a certain unit volume, right? So you could define solubility of a salt in terms of the amount of salt that would dissolve in grams per liter, or let's say grams per milliliter. And again, you would be saying X grams dissolve for every liter of water, all right? That's what we mean by solubility. We can also define something called the molar solubility. So instead of looking at grams per liter or grams per milliliter, molar solubility looks at how many moles of a salt can divide or dissolve in a liter of volume, all right? So this would be in terms of molarity. So note that there is a difference between what we are defining here as the molar solubility versus KSP. So KSP is an equilibrium constant, right? It is a measure overall of the solubility of a substance, but it is not the molar solubility, okay? Solubility, this molar solubility, is going to depend on a couple of different things, including concentrations of things that are already present, as well as pH, okay? But we can get the molar solubility, how much of the salt dissolves per liter volume, from KSP. And to do that, we are going to be essentially solving another equilibrium problem, okay? So again, purpose of this slide is to tell you KSP and molar solubility are not the same thing, but we can determine one from the other. Okay, so how would we go about doing that? So let's say that we wanted to know the molar solubility of a fairly insoluble salt, something like magnesium hydroxide, okay? Again, what we're dealing with when we're dealing with KSP is the chemical reaction where we have the solid dissolving into its component ions, and we've already looked up the KSP value for this magnesium hydroxide. So now how would we go about figuring out how much of this guy dissolves per liter volume? Okay, so we're going to set this up just like we normally have with respect to our equilibrium constant expressions. We've set up our reaction. Right, so we have magnesium hydroxide dissociating into magnesium ions and hydroxide ions. And we're going to note our initial concentrations of things. So we don't have anything, right? We don't have anything initially. So for our products, we're going to be 0 and 0. And then for our reactant, again, this is a solid, so usually we would just mark this out, all right? And so I'm going to go ahead and mark out the initial. I'm not going to mark out the change, though, because that's going to kind of be a thing in a second, okay? All right, so then if we have 0 and 0 for our two products, we're going to represent the change as this unknown variable x, right? So these guys are going to gain x, the magnesium is. The hydroxide, because of the 2, is going to gain 2x. And then, because there's a 1 in front of the magnesium, it would lose x in this process, right? So now, we go through, we're going to go ahead and sum the columns. So 0 plus x is x, and then 0 plus 2x is 2x, okay? All right, so from this, I'm going to go ahead and write out my equilibrium constant expression. So KSP is equal to the concentration of magnesium and the concentration of hydroxide squared. And so now I'm going to go ahead and plug everything I have into this, right? So I've got my KSP value of 8.9 times 10 to the minus 12. That is equal to x times 2x, but now note that that 2x is squared. So when I simplify things, I'm going to be left with 8.9 times 10 to the minus 12 is equal to a 4x cubed. Because again, everything in here is squared, so that's 2x squared times an x is 4x cubed. So as I go ahead and solve for this, I'm going to divide by 4. That gives me 2.25 times 10 to the minus 12 is equal to x cubed. And then to get rid of the cube, I'm going to take the cube root, and that's going to give me an x equal to 1.3 times 10 to the minus 4th, and that's in units of moles per liter, or just molarity. Okay? All right, so essentially what X is the solubility, right? It is the molar solubility of this salt. This is how much magnesium hydroxide dissociated into its component ions, and again, that is represented by this little x that we have just solved for. All right, so we have just calculated the concentrations of our two products at equilibrium, right? But we have also determined the overall molar solubility, how much magnesium hydroxide dissociates when you put it into a liter of pure water, okay? Okay, so go ahead and try this question on your own. Again, it's asking a very similar question as to the previous example. So they wanted to know the molar solubility of iron hydroxide now in pure water. And this also should be stated at 25 degrees Celsius. So if you want to go ahead and try this guy and then pause it and come back, I'll give you the answer after you pause it. Okay, so one of the early steps in trying to solve a problem like this would be to go in and either look up in the appendix or in that table a few previous slides ago the KSP value for iron hydroxide, iron 2 hydroxide, and so I just did that. The KSP is equal to 4.87 times 10 to the minus 17th. And so once we have that, I'm gonna go ahead and write out the actual
chemical reaction. So we have solid iron hydroxide dissociating into iron 2 plus ions, and then 2 hydroxide ions. I'll go ahead and write out my ice table, and I'll ignore my equilibrium, but note that in this change we are going to be essentially dissolving this iron hydroxide, and we're going to be determining how much of this guy actually dissolves once we reach equilibrium. Okay, so for our two products, we're going to get 0 and 0, and then we're going to gain an x, and then we're going to get a 2x for the hydroxide. So we're left with x and then 2x. Our equilibrium constant expression for this reaction is Fe2 plus times OH minus squared because of the 2. So when I plug this guy in, I'm going to be left with 4.87 times 10 to the minus 17th is equal to x times 2x squared. The only thing to note with respect to these KSP problems is always like the stoichiometry. That's the thing that's going to change. And that's why it kind of changes comparatively to the acid-base stuff that we've been doing. But other than that, it's all fairly simple. So we're going to be left with 4.87 times 10 to the minus 17th is equal to 4x cubed. When we solve for x by dividing by 4 and then taking the cube root, so 4.87 e to the minus 17th divided by 4, taking the cubed root, it's going to give us an x equal to a very tiny number. This is 2.3 times 10 to the minus 6 moles per liter, or we could also just say molar. Okay, so again, this guy would be, and when we plugged it in, we could determine the concentration of our two products at equilibrium, but also it is the molar solubility of our salt with respect to moles per liter. All right, so if we were to say, hey, what is the solubility in, let's say, grams per liter, and you could figure out from your KSP and your equilibrium stuff the solubility in moles per liter, how would you go about kind of converting this guy from moles per liter into grams per liter if we wanted something like that? Okay, so maybe think about that, and if you have a question, you should ask me. Okay, so we're going to go back really quickly. Now that we've learned how to determine the molar solubility of compounds from the KSP, I want to talk about kind of like KSP and then relative solubility of two different things, right? So just a reminder, KSP and our solubility, our molar solubility, are related to one another, but they are not the same thing. They're not interchangeable, right? We can use KSP to determine molar solubility, but you have to be careful when you're actually comparing the solubility of two different compounds if you're trying to use their KSP values to do that, right? So for example, I have already said that for KSP, we know that tiny little values of KSP essentially lead to very insoluble compounds, right? But if I took two different compounds, let's say like magnesium hydroxide and iron carbonate, and let's say I looked up their KSP values and I said, okay, well, looking at these KSP values, can I determine which one of these compounds is least soluble? You would think that you would be able to do that, right? So you'd say, oh, well, this has a smaller KSP value, so that must mean that magnesium hydroxide is the least of the two, the least soluble of the two compounds, right? Because it has a tinier value of KSP. So you would want to do that, and that would unfortunately be incorrect, right? So if we actually looked at the solubility of these two guys, we could compare the magnesium hydroxide to the iron carbonate and find that in actuality it is the iron carbonate which is the least soluble, right? When we're actually looking at how much of these two both dissolve, right? So for these two compounds, we cannot use KSP as a measure of relative solubility, right? Why is that, though? What is the difference between these two compounds? So what we will find is that it depends on the reaction stoichiometry, right? If we kind of worked out our equilibrium constant expression for something like magnesium hydroxide, which we did before, we found that KSP was equal to 4x cubed. And note that x for all of these guys is essentially the molar solubility, right? Whereas for something like iron carbonate, this breaks down in a 1-to-1 fashion, so the equilibrium constant expression would end up just being x squared, right? So the reason why we can't use KSP as a measure of solubility between these two compounds is because their reaction stoichiometry is different, right? We get essentially 3 ions that come out of this one, whereas we only get 2 ions that dissociate in this one, okay? All right, so you can't necessarily use KSP as a measure of the solubility when you're comparing two compounds if they don't have the same reaction stoichiometry. If they do have the same reaction stoichiometry, then you can use the KSP value to determine who is the more soluble of the two compounds, or who is the least soluble of the two compounds. So for example, if I took magnesium hydroxide and I compared it with something like calcium fluoride, where both of these guys dissociate into 3 ions, and they would all have KSP expressions of 4x cubed, then we could look at their KSP values and determine who is more and who is least soluble between the two. So for this guy, because again, they have the same exact reaction stoichiometry, the calcium fluoride is more soluble and the magnesium hydroxide is less soluble. We can compare that via KSP as well as the solubility. We'll find the exact same thing, okay? All right, so the only time that you can utilize KSP as a means to determine who is more soluble between two different compounds is when they break down or have the same exact reaction stoichiometry, right? Okay, so now we're going to look at a couple of different things that are going to overall affect the solubility of a salt, right? So just as a reminder, KSP is the equilibrium constant expression for these dissolution reactions, right? The solubility product constant. It is constant, right? So this value will always be constant at a constant temperature, right? So at constant temperature, this will be the exact same value regardless. Now, solubility, on the other hand, can change, and it can change depending on the things that are already present in solution, right? So one of those things that could overall affect how much of something will dissolve, or the solubility of something, is the presence of a common ion. So let's say that we had some sort of solid salt, something like calcium fluoride, and we wanted to dissolve calcium fluoride into solution, right? But let's say that that solution already had a 0.1 molar concentration of fluoride ion, right, which is a common ion, right? So sodium fluoride is a very soluble salt. We can imagine that it just dissociates into sodium and fluoride, and if there was 0.1 of these guys, because the KSP for this would be so large, we could just essentially assume that there would also be 0.1 of this guy and 0.1 of this guy, okay? So this is the solution that we are trying to put our calcium fluoride into, right? It already has a 0.1 molar concentration of fluoride. So how do you think that's going to affect the overall solubility when we're trying to dissolve calcium fluoride into this solution, right? So the presence of this guy, if we think back to Le Chatelier's principle, is essentially going to shift this reaction to the left. What does that mean in terms of overall solubility? That means that the calcium fluoride will be less soluble in a solution where it already has some of its ions present, right? So this guy shifts us back to the left. The left is solid compound, right? So again, the presence of this common ion of fluoride would make calcium fluoride less soluble. And we can calculate that effect, and I'll show you how to do that in a second. So anytime, this is what we call this common ion effect, right? So calcium fluoride, sodium fluoride, they both share the common ion, fluoride ion. In the presence of fluoride, it's going to shift the equilibria so that you don't get as much dissolving because, again, they both have this common ion in effect. So in general, we want to talk about generalities. The solubility of something is lower in a solution that contains a common ion comparatively to pure water. Okay, so what about the effect of pH, right? So let's consider the dissolution, or the dissolving of something like magnesium hydroxide. So magnesium hydroxide in water dissociates into magnesium as well as hydroxide ions, right? let's say that we're trying to dissolve this in a solution with a very high pH. So high pH, since you guys are now experts on acid-base chemistry, indicates a high concentration of hydroxide ion, which at this point in time is a common ion with respect to magnesium hydroxide. So high pH introduces our OH minus, right? This will shift the equilibrium back to the left, which means that magnesium hydroxide in a solution that has a very high pH will be less soluble. And in general, we'll find that to be true for pretty much any ionic compound that contains either a strong base, so hydroxide ion is a strong base, or a weak base as its anion, right? So strong base or weak base, we will see the solubility decrease with increasing pH or increasing basicity, okay? So again, strong base is hydroxide. A weak base is going to be any type of conjugate acid of a weak acid, or conjugate base of a weak acid. Things like fluoride or acetate, right? All of these things that we've dealt with before, these conjugate bases of weak acids, these are all weak bases, right? So again, if you have a salt, something like, let's say calcium fluoride, when you try to dissolve it in a solution that has a high pH or a high basicity, then you will see that it won't be able to dissolve. It will be less soluble in that type of solution comparatively to water. Okay, so that was in a high pH solution, right? Lots of hydroxide ions. Now let's look at the solubility of the same thing, this magnesium hydroxide, in a solution that has a very low pH, right? So low pH means that you've got not a lot of hydroxide, but instead you've got a lot of H3O+, right? Remember that H3O+ reacts with hydroxide, right, to form just nice plain water, okay? And so because of that, if we're trying to dissolve something like magnesium hydroxide in a solution with a bunch of hydronium ion, that hydronium ion is going to react with OH minus. It's going to produce water in the process, which is going to remove OH minus from solution, right? So if we remove this guy from solution, then this equilibrium, going back to the Chatelier's principle, is going to shift to the right to replace what it's losing in this reaction with hydronium ion, right? So long term, what this means with respect to solubility is that you will see an increase in solubility for salts that contain either a strong base or a weak base when we increase the acidity or we decrease the pH, right? So low pH, we're going to see an increase in the solubility of these compounds that contain either hydroxide or some sort of weakly basic anion. Okay, so let's go ahead and try to apply what we've just learned with respect to this common ion effect. So let's say that we want to calculate the molar solubility of calcium fluoride in a solution that contains 0.25 molar calcium nitrate. Okay, so as a note, calcium nitrate is very soluble, has a very large KSP. So just like we could assume in acid-base chemistry that strong acids completely ionize, we can also assume that things with large KSPs just completely dissociate, right? So this calcium nitrate will dissociate into calcium ions and nitrate ions, right? And if we have a 0.250 molar solution of this guy, that means that we form a 0.250 molar solution of calcium, as well as a 2 times that, right? Because for every one of these, we get 2 of these, a 0.500 molar solution of nitrate ions, okay? So that's number 1, because we have, again, the presence of a common ion here. All I'm trying to figure out is how much of this common ion, this calcium ion, we are given by this original solution, this original calcium nitrate solution, okay? So now the question is, how does this guy affect the solubility of calcium fluoride? So now I'm going to take my calcium fluoride solution, and I'm going to write out the expression for it. So calcium ions plus 2 fluoride ions And I'm going to go ahead and draw my little ice table here, okay? So again, we don't care about the solids, and I am going to go ahead and represent this as this change because there's a 1 here, so this is going to be a minus x. But now the big difference, and the way this gets affected by this common ion, is instead of assuming that we have 0 calcium initially, we don't have 0 calcium, we have 0.25 molar calcium initially. So I'll go ahead and plug that in. So we've got 0.250, and we have 0 of this guy. Right, so now everything else is the same. We'll have a minus x, or no, plus x, pardon me, and then plus 2x. And then at equilibrium, we'll have 0.250 plus x, and then we'll have a 2x. All right, so then you go up and you look up the KSP value for this calcium fluoride. KSP here ends up being equal to 1.46 times 10 to the minus 10th. So 1.46 times 10 to the minus 10 is equal to a 0.250 plus x, so that's my calcium, and then 2x squared. Okay, so again, this is going to be very, very tiny. KSPs are very small usually. So because of that, to make the math a little bit more simple, we're going to ignore this x addition to the 0.25 because again, x is going to be very small, and comparatively to 0.25, it is going to essentially be almost negligible. Right? So when we ignore that, we're going to be left with a 0.25 times 4x squared. So when I multiply those guys together, 4 times 0.25 gives me a 1. So this is going to be 1.46 times 10 to the minus 10th is equal to x squared, right? Because this times this is just 1, so I'm just left with my x squared. I'm then going to take the square root, so 1.46 e to the minus 10th, take the square root of that. It's going to leave me with an x equal to 1.2 times 10 to the minus 5. And that's in moles per liter. Because again, what they're asking us here is what is the molar solubility, this guy, for calcium fluoride in a solution that contains 0.25 molar calcium, common ion. And so we found that this is the molar solubility for calcium fluoride in this solution. So again, if we had compared that to just calcium fluoride by itself, right? So calcium fluoride in pure water, everything would have been the exact same. So it would be the exact same KSP because that's a constant. But instead of all of this stuff, we would have just been left with 4x cubed. So when we solve for x, which is again the molar solubility, 1.46 e to the minus 10th divided by 4, and then take the cubed root, we would have gotten a molar solubility of 3.3 times 10 to the minus 4th moles per liter, right? So in pure water, calcium fluoride is more soluble than it is in a solution that contains a common ion, right? Which is what we just said, going back to Le Chatelier's principle. So it's a nice little demonstration of that fact. Okay, so why don't you go ahead and give this question a try. It's very similar, right? We're dealing with a common ion effect, but now we're going to the concept of pH with respect to the common ion. So I want to know what is the, so we want to know the KSP for this compound. So we have magnesium hydroxide, and we put it into solution, dissolve it, and produce a saturated solution, so it's at equilibrium, and it's found to have a pH of 10.17. So I want you to utilize this data to calculate the KSP for this compound. So this would be kind of like the reverse. Just as a reminder, before you give this a shot, pH is equal to minus log of H3O plus. Also, pOH which is mainly more important here, is equal to minus log of OH minus. So it may be smart to determine the pOH for the solution and then maybe determine the hydroxide ion concentration from there. So go ahead and give us a try and then push play again and I'll show you the answer. Okay, so with respect to how you would go about doing this, right? So I'm going to go ahead and write out my reaction. So my magnesium hydroxide, it's in a saturated solution, so we're at equilibrium with magnesium ions and then 2 hydroxide ions. And I'm going to go ahead and draw out my ice table. And for this guy, I'm just going to ignore it because we don't care about, we're not looking for molar solubility here. I'm also going to go ahead and write out my KSP expression. So we've got KSP is equal to the concentration of magnesium at equilibrium times the concentration of hydroxide at equilibrium squared. Okay, so the big idea here is we need to figure out what this guy and this guy are so that we can plug them in and get the KSP. Okay, so one thing that we can already note, there is no common ion, there is nothing in solution initially. So initially we have 0 and 0. And then when we put this into solution, it makes a solution with a pH of 10.17. So what pH is going to tell us here, and this is what I tried to hint at, is overall the concentration of hydroxide ion. So if my pH here is 10.17, then my pOH, so pOH, which is just 14 minus pH, is 3.83. And so if 3.83 is equal to pOH, that is equal to minus log of OH minus. I can go ahead and solve for concentration of OH minus by moving over the negative, and then this is 10 raised to the minus 3.83. It's going to give me, oh darn, I should have kept that. 3.83 minus 10 raised to that is going to give me a concentration of 1.48 times 10 to the minus 4th molar. So that is essentially telling you the concentration of OH minus at equilibrium. So I'll go ahead and come back over here and write that in for my OH minus. So this is 1.48 times 10 to the minus 4. And the only thing to note here is that to get from here to here, we have to have gained 2x, right? So 2x is equal to 1.48 times 10 to the minus 4. This guy would have only gained x. So I'm going to go ahead and solve for x by dividing my 1.48 by 2. That gives me a 7.39, no, 7.40 times 10 to the minus 5th. And so that guy is what magnesium is. Okay, so now I have my concentrations at equilibrium. I can go ahead and plug them in. So this is 7.40 times 10 to the minus 5. And then this is 1.48 times 10 to the minus 4. That's squared. And overall I get a KSP here, 1.62 to the minus 12. Okay, so I think this was kind of out of order. I think I should have done this one earlier. But again, how would you utilize the concentration of one of the products to figure out the KSP? So you would do your little ice table, figure out the concentration of one, figure out the concentration of the other, and then plug it into your KSP expression. All right, so these are kind of popular little types of problems. So barium sulfate is fairly insoluble. The question here is which solution is barium sulfate most soluble, right? So we have three different options here. Two of the options contain a common ion. One of them doesn't, so give this a second, think about it. Again, we're looking at where barium sulfate is most soluble. Okay, so I'm going to go ahead and just write out really quick. You probably know the answer already, but I'm just going to go ahead and write out my barium sulfate. It's dissociating into barium ions plus sulfate ions. And the question I'm asking is, in which of these three solutions will this go farther to the right? Right? Which of these solutions will produce more of these guys at equilibrium? So in the first solution, in A, we are doing this in the presence of 0.1 molar barium, which comes in the form of barium nitrate. So the presence of a common ion always pushes this equilibrium back to the left, meaning it's less soluble. Most of it stays as a solid, or more of it stays as a solid. So less soluble whenever we go back to the left. So this would not be good. Number two, we've got 0.1 molar sulfate, so this is another common ion. Again, so we'd be putting this in the presence of 0.1 molar of this guy, which would again push it back to the left, meaning it's less soluble. What did I write over here? Less soft? Okay. I'm not quite sure what that means. Less soluble. Left means less soluble. So both of those first two, A and B, presence of a common ion decreases the solubility. And so then in C, we have sodium nitrate. Sodium nitrate is not in any of these guys, so that's not going to affect the solubility at all. And so it would be most soluble in sodium nitrate, because again, there is no common ion with respect to that salt. Okay, so in last question, I'm going to determine whether or not each of these compounds is more soluble in an acidic versus a neutral solution. So I give you three different compounds. So again, think about this one for a second, and then push play again, and I will give you the answer. Okay, so for each of these, we're again looking at whether or not these are more soluble in an acidic versus a neutral solution. And so if we looked at the first one, we've got barium fluoride dissociating into barium 2 plus 2 fluoride ions. So if we were in an acidic solution, so acidic solution have a bunch of hydronium ions, so I'm just going to represent that as H plus. The H plus would react with things that are either strongly basic or weakly basic and remove them from solution by forming either water or the conjugate acid, right? So hopefully you realize that fluoride is the conjugate base of a weak acid. So the weak acid is HF. This is the conjugate base. So that means that it is weakly basic. So in the presence of something like H+, it will react, so plus H+, it will react and form its conjugate acid, right? And what that does is it removes this fluoride from solution, right? It's in the form now of this little weak acid, which is removing the concentration that we had of fluoride ions. If we are removing something, going back to Le Chatelier's principle, then this reaction is going to want to shift in a way to replace what it's losing in that process. And so by doing that, we are going to essentially dissolve more of our barium fluoride solid into barium ions and fluoride ions, right? So what that means in terms of solubility is that this would be more soluble. More of it will dissolve to replace the fluoride ions that it is losing in this reaction with the hydronium ions forming HF. So any type of salt that has a weakly basic or strongly basic anion is essentially going to be more soluble in a lower pH in a more acidic solution. So A would be more soluble in an acidic solution. So for B, silver iodide. So iodide, hopefully you guys remember from last week, iodide is the conjugate base of HI, which is a strong acid. Right, so strong acids produce negligible bases. And so because of that, iodide won't react with hydrogen ions or H+, and so it won't be removed from solution the same way that the F- was. So I would say that this would be more soluble in a neutral solution because, again, it won't react with the H+. So that's kind of a weird way to state this. I think it's mainly asking, like, oh, which one of these would be more soluble in an acidic solution? But for AgI, this would be the same solubility whether or not it was in an acidic solution or a neutral solution. And again, that's because iodide, its anion is a negligible base because it is the conjugate base of a strong acid. So, no. We have the same solubility in both of them. Okay, so then last one, we've got calcium hydroxide. Same exact concept here. Calcium hydroxide going to make calcium ions plus hydroxide ions. If we add a bunch of H+ in an acidic solution, it's going to react and form water. That's going to remove our hydroxide ions. And so this guy's going to shift to the right to replace what it's losing in that reaction. And by doing that, it makes it more soluble. Because again, the anion here is now, instead of a weak base, it is a strong base. So this would be more soluble in an acidic solution. Okay, all right. Okay, so last little brief topic. We're going to come back to this idea of precipitation reactions, okay? So in chapter 4, or whatever chapter it was, back in 151, we would have these precipitation reactions, right? This was a form of a double displacement reaction where you would take two reactants, so let's say something like lead nitrate and sodium bromide. They were two completely soluble compounds, or very soluble compounds, right? They were listed as soluble on our solubility chart. And when you mix them together, if you formed a compound that was insoluble, you would get a precipitation, right? And so how would we do that? So we take our two reactants, we would switch their partners, right? So I would have, let's say, break this guy into its component ions. I would have lead and nitrate for this guy. I would have sodium and bromide. And to figure out if I made something that was insoluble, I would switch their partners. I would predict the neutral compound for the new thing. So this guy would be sodium nitrate. And then this guy would be lead bromide. And since it's Pb2+, it'd be lead with two bromides. And then I would write them up here as their little cells, and I would look up whether or not they were soluble in the solubility table. So sodium nitrate, if we looked in the solubility table, would be soluble. Lead bromide, though, would not be soluble. They would say, oh, lead bromide forms insoluble compounds. And so we would write that as a solid, and that would be great. That would be our precipitation reaction. We predicted that by exchanging the partners of the two reactants, right? Okay, so again, that's the problem with chapter 4. We gave you this very black-white answer with respect to solubility. It was either insoluble or it was soluble. And if it was soluble, it stayed in solution forever. If it was insoluble, it immediately precipitated at the first sight of any type of ions that you could ever put in there. Right? So that is not real, or it's kind of a simplification. And instead, this idea behind precipitation is going to come back to some of the concepts that we've learned with respect to equilibrium. So because of that, to determine whether or not something is going to precipitate, we're going to have to consider what Q is relative to what K is for the molar solubility, not molar solubility, for the solubility product constant, right? So what was Q? Does anyone remember what Q was? So Q was the reaction quotient, right? So this was the reaction quotient. It was the, so that says reaction. I realize that you probably can't read that at this point in time. So again, what was the reaction quotient? Well, it was the exact same thing with respect to what K is, right? So K is just the equilibrium constant expression. Q took on the exact same form, except for Q, the concentrations were not at equilibrium. Right? So for Q, you had to have concentrations at equilibrium, whereas for K, you had to have concentrations that were at equilibrium, whereas for Q, you could be anywhere, and you could figure out where you were going to go with respect to equilibrium, depending on what Q was relative to K, right? So if Q was less than K, then we would see the reaction going to the right, whereas if Q was greater than K, we would see the reaction going to the left, right, to get to K, right? So we're going to use that same type of concept with respect to precipitation, whether or not we're actually going to see a precipitate form. Now, with respect to solubility, what that's going to translate into is that if Q is less than K, then that means that we have not reached a saturated solution yet, so more solute can dissolve before we actually do reach saturation and we see precipitation. So Q less than K, this means no precipitation. And then if Q is greater than K, then we do have a saturated solution, and you would expect that then to precipitate. Right, it would shift back to the left to get back to equilibrium, which is the solid. Right. All right, so Q less than K, we're not going to see precipitation. We can have more solute dissolve. It shifts to the right. Q greater than K, it'll shift back to the left. We'll see precipitation. We'll see the formation of a solid. Okay. And then there's also a special case where we are right at K. This is what we call a saturated solution. So that means that, yeah, no precipitation, I guess. But there would be some solid. So it's not going to be, hopefully it'll all be very cut and dry. It's either going to be Q less than K, Q greater than K. Okay, so how would we actually utilize this in a problem? So we have a solution where we combine lead nitrate, right? So I'll go ahead and write this guy. We've got lead nitrate. And it's fully aqueous, so very soluble. It's mixed with a solution containing sodium bromide. So this is with NaBr. And we want to know, so we give the various concentrations of these two, we want to know whether or not a precipitate forms, right? So going back to these double displacement reactions, what precipitate would that be? Well, we could look at our possible products. So if I break my lead nitrate up into its component ions, and I do the same thing for my sodium bromide, I will find the production of sodium nitrate, which is very soluble, very large KSP. So this would not be something that we would consider precipitating. But on the other hand, this guy, PbBr2, lead bromide, lead-2 bromide, is fairly insoluble. It has a KSP equal to 4.67 times 10 to the minus 6. Right, so now the question is, when I combine these two guys and I give them the following concentrations, so they're going to form a solution that is 0.015 molar lead nitrate and 0.0035 molar sodium bromide, do we actually get a precipitate formed? Okay. And so now what we're going to be looking at is Q relative to what K is for lead bromide. I'm going to go ahead and just write these guys up here. Aqueous, and then Pb, Br2, and then question mark solid. We'll find that out. Okay, so also I just want to go ahead and just briefly balance these because that disturbs me if I don't. Okay, so now the big question is, we're looking at Pb, and we're looking at 2 Br minus coming together. Okay, well, I want to know what the concentrations of these guys are to form this lead bromide. Okay, so they tell me that they mix these two in a way that forms a solution that is 0.0150 molar lead nitrate and 0.0035 molar bromide ion. And so again, with respect to this guy, sodium bromide, it's only going to break down in a 1-to-1 ratio. So if there are 0.0035, then you're going to get 0.0035 of this guy, right? So even though there's a 2 in front of this, it's coming from something that's only going to give us this much. All right, so we'll go ahead. I've written this in reverse, which may be confusing. So we're looking at the solubility of this guy. So PbBr2 breaking down into Pb2 plus Br minus, and there's a 2 in front. And right now we have concentrations of these guys at 0.0150 and 0.00350. So the question is, what is Q? And what is Q relative to K? Because we've already looked up K. So I'm just going to take these guys, I'm going to plug them in to the reaction quotient expression. So this is just Pb2 plus times Br minus squared. So when I plug these guys in, I get 1.015 times 0.0035 squared. And this is QSP. And when I do that, I get a number that is 1.84 times 10 to the minus 7th. Okay, so when I compare this back to my KSP, I will find that Q at this point in time is less than my value for K, right? So what that means is that we will not see precipitation because we can still add more of our 2 ions and before we ever see this guy shift to the left and make solid, okay? So because Q is less than K, there's no precipitation. If Q was greater than K, then we would have seen precipitation. But we didn't. So this is the big, oh yeah, that's good. That's great. So this is the big answer. Q is less than K, no precipitation for this reaction. Okay, and so I think that's it. That's all the slides. So there's not going to be a quiz that is associated with this, but I am going to open up the homework for KSP. And so if you have questions, I would consult this video, I would consult your textbook, or you can also email me with respect to any of the problems that are in the homework.